Morning students. Now we'll go to Clapeyron-Clausius equation. Okay, Clapeyron-Clausius equation is the same like Clapeyron equation only, but we take three limiting conditions. One is we are applying it only to liquid vapor system. We are not applying it to any other physical equilibrium systems. For example, solid to liquid or solid to vapor, etc. We are doing it only to liquid vapor equilibrium. Now then next one is volume of vapor is taken, or it is always much greater than volume of liquid. Then third one, this vapor will be behaving as an ideal gas. So these three limitations we are applying to Clapeyron, and now we got Clapeyron-Clausius equation. Okay. Now we know dP by dt for a liquid to vapor equilibrium. dP by dt is equal to delta SV divided by delta V, which we can write it as delta HV divided by TB. You can write, okay, boiling point into VV minus VL. And we are going to apply the assumptions. One is volume of vapor is much greater than volume of liquid. So volume of liquid we are going to neglect here. Neglect means consider pannada. So V minus VL is our delta V. So delta V will become V, that is vapor, volume of vapor alone. For example, if you take the case of water at a particular temperature, if the vapor's volume is 30,060 ml, corresponding liquid's volume is only 18 ml. This is the volume VV and this is the volume of the liquid. So see, if you take 30,060 minus 80, it is coming as 30,042. That is very small difference. So we can take, instead of minusing this, it is just 30,060 itself. What is the reason is this value is very high. So that is only, so volume of vapor minus volume of liquid is taken as volume of vapor. Okay. Now what happened to the expression? Expression will become dP by dt is equal to delta HV divided by TB into VV. Okay. Now we will use the second assumption. What is the one? This vapor will be acting as an ideal gas. So we'll use ideal gas expression for n moles. PV is equal to nRT. So we can write it as nRT divided by P. This we can substitute in equation 2. So what happened? dP by dt is equal to delta HV into T into nRT divided by P. So what happened? P we can bring it either to the up or to this side. So P into dP by dt is equal to delta HV by nRT square. Okay, P we are bringing it to the other side. And we'll consider for 1 mole now. So 1 mole means N is equal to 1. So we can write P dP by dt is equal to delta HV by RT square. This is the differential form of Clapeyron-Clausius equation. Okay. Now what is the expression? It is P into dP by dt is equal to delta HV divided by RT square. This is for 1 mole. So P into dP by dt we can also write it as d ln P. ln is log to the base E. So delta HV by R dt ne we brought it to the right hand. dt divided by T square. So either of this you can take it as the differential form of Clapeyron-Clausius equation or Clausius-Clapeyron equation. Now we will go for the integrated form. Integrated form means we are going to integrate this. We are going to integrate within the limit of temperature T1 and T2 and pressure P1 and P2. So we write integration. This is the sign P1 to P2 d ln P is equal to T1 to T2 delta HV by R dt by T square. Now this is a constant, so we take it outside. Delta HV by R is equal to integration T1 to T2 dt by T square. And dt by T square, we can write integration when we take, we can write it as 1 by T square is written as T raised to minus 2 dt. So when we integrate this, what is the solution is minus 2 plus 1 T minus 2 plus 1. So minus 1 into T raised to minus 1 will come. So we wrote it as minus 1 by T. So when we come back to here, we can write delta HV by R is equal to minus 1 by T, T1 to T2. Then D ln P, the solution is ln P only. So P1 to P2. So applying the limit, we will have, what are the things? Ln P2 divided by P1 is equal to delta HV by R, the square bracket, minus T2. 1 by T2 minus 1 by T1. We can take this minus sign inside. So it will become 1 by T1 minus 1 by T2. So ln P2 divided by P1 is equal to delta HV by R into 1 by T1 minus 1 by T2. This is the integrated form of Clausius-Clapeyron equation. So Clausius-Clapeyron equation is Clapeyron equation only, but we are deriving it taking 3 assumptions. We are applying only to liquid to vapor equilibrium. Volume of vapor is greater than volume of L. So delta V will take it as V minus VL is taken as volume of vapor alone. Then this vapor will behave ideally, that we assume. So based on that, when we do the assumption, dP by dt is delta SV by dV, delta HV by TB into VB minus VL. So this will become V. So expression will become dP by dt is equal to delta HV by TB into VB. We apply ideal gas expression. So we got P into dP by dt is equal to delta HV n RT square. Taking for 1 mole, it is P into dP by dt is equal to delta HV by RT square. This is the differential form. Now we just rearrange it. This can be written as d ln P and T is brought to the other side. So delta HV R by dt T square. So this is also, you can call it as differential form. Then we are integrating within the limit. We got the value ln P2 by P1 is equal to delta HV by R into 1 by T1 minus 1 by T2. So this is the integrated form. Okay, so students, please write down several times and study the derivation properly. Then only for the exam you will be able to write. So do as an assignment, study this derivation part of all the things, Clapeyron equation, apply it to the 4 different types of physical equilibria and Clausius-Clapeyron equation properly. Write it or do it without seeing. Do yourself and post it to me. Okay, hope you have understood it. Otherwise, see the videos again and again, or you can contact me. Okay, thank you.